Hi, so this is the 8.2 practice problem review video. I didn't give you problems at the end of the 8.2 lesson. That lesson was recorded for a previous semester before I started doing these practice problem review videos. So these are the problems I'm going to work through in this video. Now, this is a lot of problems, a lot more than I normally include in review videos, but I know quantifiers are hard and predicate logic includes a lot of new things, so I am going to work through all of these. I don't expect you to watch every single problem. The way that I'm hoping you'll use this video is that you go try these problems on your own and then come back and just watch the ones that you want to see me go over. So I'm going to go ahead and get started. The first one is 2a. Some integers are odd and some are even. So this is the symbolization key provided in the textbook. I'm going to keep it right here on the side. So now we've got two of the indication words, right, that let us know we're going to be using quantifiers. Some integers are odd, and then we have the conjunction, and then some are even. So we know we're going to be using two quantifiers. And here that's going to be two existential quantifiers, right? We're just saying that some are odd and some are even, not anything about all positive integers. So the truth functional paraphrase looks like this for me. There is some such x such that x is odd, and there is some such x such that x is even. Now I have those there is some such x phrase in italics because those are our existential operators. And then the and is in bold because that's going to be our main connective, right? The scope of each of those existential quantifiers is limited to the claim right next to it. It doesn't range over the whole sentence. So the symbolization we get looks like this, right? There exists an x such that x is odd, and there exists an x such that x is even. That conjunction is the main connective, and again, we don't have to worry about parentheses for the scopes of those quantifiers because they only apply to that predicate sentence right next to it. The next is no positive integer is less than 1. There's a couple of ways we can do this, right? We talked about problems that say no something is something else in the lesson video. So one way to do this is to say, for every x, it is not the case that x is less than 1, right? For every single positive integer, that positive integer is not less than 1. When we do that, we'll symbolize it like this, right? For all x, it is not the case that x is less than 1. 1 here has been assigned the individual constant a, and we have that two-place predicate lxy for x is less than y. So we need to have the x first here after the L predicate to say x less than 1, and then we have that negation to say it's not the case that x is less than 1. We also could have done it this way. It is not the case that there is an x such that x is less than 1, right? We say there is some x less than 1, and there is some x less than 1, and then we add the negation to the front. So that symbolization would be this, right? It's not the case that there exists an x such that x is less than 1. These two formulations are logically equivalent. Either one of them you choose to use is fine. Now we have 2 is less than 4, and 4 is less than some positive integer. We have that word some, so we know we're going to need an existential quantifier in here somewhere. We've got two separate claims, right? That 2 is less than 4, and then the claim about 4 and some positive integer that we know we're going to need a quantifier for. So the truth functional paraphrase, we have 2 is less than 4, and then that and is our main connective, right? And then because we have some, we're going to say there is an x such that 4 is less than x. So now we look at our symbolization key, right? We have lxy, and then we know that 2 is b and 4 is c. So that first conjunction is going to be lbc. And then we say there exists an x such that 4 is less than x. So now we have c, that individual constant for 4, in the first place after the L, and the x in the second place, so that 4 is less than x. And again, that existential quantifier only modifies the x in that one two-place predicate, so we don't need any extra parentheses. Next, we have not all positive integers are prime and not all positive integers are even. So we already talked about not all. We already talked about no cases, right? No positive integer is, no positive x is a y or whatever. Now we're going to talk about not all statements. So the main connective here is the and, right? So I'm going to break this down and do one conjunction and then the other. First, we're going to do not all positive integers are prime. One way to do this is to say there is a positive integer that is not prime, right? That paraphrase would be there is some such x such that it is not the case that x is prime, right? If not all positive integers are prime, then there is some x that is not a prime. Our symbolization looks like this. There exists an x such that not px. Now the second one takes the same form, right? Not all positive integers are even. We could also do this by, but I'm going to show you the other way to symbolize this. So we could do this by saying all positive integers are even and then adding a negation to the front. So the paraphrase here is, it is not the case that for every x, x is even. It's not the case that for all x, ex. These two are also equivalent symbolizations, or equivalent ways of symbolizing this, right? One we're saying even, one we're saying prime, but both of these sentences have the same form. We could have said there exists an x, not the case ex for the second one, and we could have said it's not the case that for all x, px for the first one. I did them differently to show you the two ways of doing it. And now to finish off this sentence, we need to go back to our main sentence and add that conjunction, right? So here, because I showed you both ways and did each side differently, this is our final symbolization. Now we have 2i. All positive integers are even if and only if all positive integers are not odd. So we know we're going to have a biconditional, right? And that biconditional is going to be our main connective. And then we have two all claims, one on each side of that biconditional. The first, all positive integers are even, and the second, all positive integers are not odd. So our paraphrase is going to look like this. For every x, x is even, if and only if, for every x, it is not the case that x is odd. Here, the main connective is that biconditional. The scope of each of those operators, the universal quantifiers, only govern its side of the biconditional, right? For every x only governs x is even, and then the second for every x only governs the it is not the case that x is odd. So our symbolization looks like this, right? For all x, x is even, if and only if, for all x, it is not the case that x is odd. Last one in this set, there is a positive integer that is less than 100. This one is easier than the last couple. There is a positive integer really clearly becomes there is an x such that, right? That's a really clear way of telling us that we're using an existential quantifier. And then we need to say x is less than 100. We have that lxy, x is less than y. So what we need to do here for our symbolization is put in that existential quantifier, put x in the first place, and then d for 100 in the second place, so that this sentence says x is less than 100, d being the individual constant for 100 in our symbolization key. Now let's look at these from 3a, right? We have a symbolization key, universe of discourse, the set of seniors at Dartmouth College, right? This is really different from the universe of discourse we had in the problems for 1 before we were using quantifiers, when the set was just Bob, Carol, David, and Emily. But other than that, our key here is the same. So the first we have is all of those who graduate will get jobs, right? So this says everyone who graduates will get a job. We're going to symbolize this just the way that we do the other all statements we've looked at so far. For every X, if X will graduate, then X will get a job. Here that universal quantifier is the main connective, so to say, of the sentence, right? The existential quantifier here for every X governs both the X in the antecedent and the X in the consequent. So to make sure we have that scope captured in our symbolization, we need to add these parentheses, right? For every X, if X will graduate, then X will get a job. And our symbolization looks like this, right? For every X, if X graduates, then X will get a job. And this makes it the case that for each individual thing we pick to look at, we ask, do they graduate? And then if so, it entails that consequent that they get a job. If at least one senior graduates, they will all graduate. Now, this is one that you've already looked at when we were not using quantifiers, right? This problem gets large and cumbersome not using quantifiers, but it's much easier this way, right? It's a much shorter problem. So we have at least one, right? So we know we're going to be using an existential quantifier, and then we have they will all graduate. So we know we're also going to be using a universal quantifier. Here, the range of those quantifiers is separated, right? The truth functional paraphrase here, sorry, that went the wrong way. The truth functional paraphrase here is, if there is some X such that X will graduate, then for every X, X will graduate. And that main connective is the material conditional. The scopes of those quantifiers are limited. So our symbolization looks like this, right? If there is some X such that X graduates, then for every X, X will graduate. If there is any one person who graduates, right? That's if at least one senior, then they will all graduate. Next, we have if anyone joins the Army, both Carol and David will. Now, here that anyone seems to be making a claim similar to someone, right? This is not a universal claim. So we're going to use an existential quantifier. If there is some X such that X will join the Army, then Carol will join the Army and David will join the Army, right? That material conditional is our main connective, right? If anyone joins the Army with the X is contained just to the antecedent, and then we have the consequent, Carol will join the Army and David will join the Army. So I'm adding parentheses here, right? Because that conjunction itself has a connective, right? It has that and in it. So we want to make sure we capture this whole second bit as the consequent. So the symbolization looks like this. If there exists some X such that X joins the Army, then Carol will join the Army and David will join the Army. Now we have each senior will either graduate or not graduate. Each is very similar to all. We've got, right, so here we're making a universal claim that for every senior, they will either graduate or not graduate. This is different from they will all graduate or they will all not graduate, right? This is making a claim that for each individual, this disjunction is true. So we phrase it like this. For every X, X will graduate, or it is not the case that X will graduate. And here, both of those X's, right, that whole disjunction is within the scope of that universal quantifier. So we symbolize it like this. For every X, they will either graduate, or it is not the case that X will graduate. So this disjunction is true for every senior in our universe of discourse. Again, this is really different from if we had said for all x, gx, or treating the disjunction as our main connective for all x, not gx. That would say either everyone graduates or no one does. So it's really important to pay attention to scope and meaning. That's the last of the problems I'm reviewing in this video. Next time, we're going to get into some more complicated quantification where we have quantifiers that overlap in scope when we have one quantifier in the scope of the other. So definitely make sure you're familiar with this part now, and we'll get into that next time.